Alright, here we start getting to some tougher problems because we're introducing more than one force. So in this situation we have a roller coaster in a circular loop. And now real roller coasters are not perfectly circular, but let's just assume this is. Let's assume I actually managed to draw a perfect circle here. So let's start with, why don't we start with the top. So the cart is at the top of the loop. And at the top of this loop, we say what forces are acting on it. So first, there is a weight force, a gravitational force pulling it down. In addition, there's a force of contact between the cart and the track. And if the car is hitting the track, we say which way is it pushing it? Well, the track's going to be pushing it down. So we say the normal force, Fn, is acting down. So those are the two forces acting on the cart at this point. Now, at this point, we say, all right, what else do we know about it? The cart's mass is 200 kilograms. That is not going to change. And at this particular speed, at the top of the loop, its velocity is 17.3 meters per second. And according to this, the radius of the loop is 20 meters. So the first thing they want us to know is, at the top of the loop, what is the acceleration of the cart at the top of the loop? And so if this is traveling in a circle, as it claims to be, right, the cart's going to come through and it's going to go around in a circle, then the acceleration is simply centripetal acceleration. So the acceleration is simply v squared over r, and that will tell us the acceleration at the top of the loop. So in this case, it's 17.3 squared over 20. And so if I calculate that, the acceleration of the cart is about 14.96 meters per second squared at the top of that cart. That is how much it is accelerating around. The next thing it says, okay, what is the net force on the cart up there? And again, basically the way we can do this, we can either use the centripetal acceleration equation, mv squared over r, and plug in from scratch, or we can recognize that, hey, if I have the acceleration of the cart from Newton's second law, F equals m times a, so I can just multiply this acceleration by the mass. And it's really exactly the same thing, because this is the acceleration, this is the mass. That's all I'm doing. So the centripetal force on the cart is 200 kilograms times the acceleration, 14.96. So 14.96 times 200, and I get that the centripetal force is 2992 newtons. And which way does the centripetal force point? It's always towards the center of the circle. So I'm going to draw that off to the side, just because I don't want anyone to think there's a third force here. There is not. So there is a separate centripetal force, not a separate force, but the overall centripetal force. This car is feeling 2992 newtons towards the center of the circle. But we're not done. The question's saying, what is the normal force on the cart? So we want to know this force. So what it is these two forces together, the gravitational force and the normal force, are causing the centripetal force. The centripetal force is the net force in this situation. So if I want to find the normal force, I first have to find the gravitational force. Well, we know how to do that. We have a 200 kilogram object, and again, I'm assuming g is 10 to make this easier. So a 200 kilogram object has a weight of 2,000 newtons. And if you need a review on that, check one of my other videos. So that means that this force is 2,000 newtons. So then the question is, well, what's the normal force? Well, I need to somehow acquire a force of 2992 downward. 2,000 of that is covered by gravity, so the normal force then must be 992 newtons downward. Because if gravity pulls downward at 2,000, then this pulls down at 992 to give me this overall force. And so together, they give you the centripetal force. So the bottom line is the centripetal force is a combination of these two forces. Now we're going to look at the bottom of the cart. Or rather, the bottom of the loop, I should say. So I've deleted everything else because it was getting in the way. So now we're at the bottom of the cart, and we say what forces are acting on the cart here. So once again, there's a gravitational force, and that always points downward. But what direction is the normal force now? Now the cart's in contact with the track here. The normal force is actually now pushing upward on the cart. And so once again, we can go through this. Now the cart's speed at the bottom is actually different than the speed at the top in this situation. That all depends on the type of motion. Sometimes the speed is the same throughout. In this situation, it's not because the cart slows down as it goes up the hill. But neither here nor there. What do we know? So the mass of the cart hasn't changed. It's 200 kilograms. The velocity in this situation is 33.2 meters per second. The radius hasn't changed. It's still 20 meters. So what is the acceleration of the cart down here? Once again, the acceleration is v squared over r. So in this situation, it's 33.2 squared over 20. And so if I calculate that out, 33.2 squared divided by 20, I get 55.1 meters per second squared. So these don't seem like realistic numbers for an actual roller coaster. That's about 5 G's at the bottom. That seems a little high to me, but maybe not. So anyway, that's the acceleration of the cart at the bottom of the track. All right, now we're trying to find the net force. So the net force, again, F equals m times a. That's the net force. So we can say, okay, 200 kilograms times 55.1 meters per second squared, and I get my net force is 11,020 newtons. Okay, so I've solved that. I've solved that. And again, if I just wanted to go straight to the net force and skip the acceleration, I could just plug in my formula for centripetal force, Fc equals mv squared over r. Gives you the same result. Okay, so that is the net force. What direction is the net force? Well, again, it's traveling in a circle, so this thing is experiencing centripetal force, centripetal acceleration, so the overall net force is towards the center of the circle. So this 11,020 newtons is towards the center of the circle, in this case up, because we're at the bottom. The force of gravity is what we thought it was before, not thought it was, what it was, 2,000 newtons. So the question is, what is the normal force that when you combine with the gravitational force, you get this in the upward direction? So the trick here is that the normal force, we don't know, but we're pushing down at 2,000, and I somehow have to result in 11,020 up. So what force is this going to be? Well, it's not. It has to be at least 2,000 just to cancel the gravitational force. Then I have to also get 11,020 upward. So the normal force then is going to be the sum of these, or 13,020. That is the normal force. Because when you take this force and you cancel it with the gravitational force pulling downward, you end up with this force. So in this case, the normal force is significantly higher than the gravitational force. In the other situation, the gravitational force was larger than the normal force. But again, all it comes down to is you can think of the centripetal force as being the net force, and your two forces, whatever direction they may be, need to cancel out to give you that as an overall result. So they're either, in this case, they're opposing each other. When it was at the top, they were actually helping each other. They were both pointing downward towards the center of the circle. So this is probably one of the tougher problems you would deal with. But if you're keeping track of all your data very carefully, then I think you should be all right. So try a few practice problems with this. So until next time, I am Derek Genova. Have a delightful day.